The track A teams are going to have 10 minutes each. The track B teams are going to have 5 minutes each. The reason that they can have so little time is because there are so many of them. And so many is good, so little time not so good. But I will not introduce you. What we will do is we will have people line up in a pipeline here, at least 3 teams to get ready to come up. Bob here is going to keep you to the clock exactly, and when he says stop, you stop. And then you get off the stage, the next person comes up. There will be a microphone here with a clip that's going to be used for the webcast, and as quickly as you can, get started on the next one. And that's what we're going to need to do in order to get through them. Again, the purpose of this is not for the government. We already know who you are. We've read all of your proposals. The purpose is to show each other what you're doing, and also to show all the people that are watching on the webcast. At present count, there are 250 people watching. So, and of course, maybe several around each one of those screens. So, this is a wonderful event. We want you to take advantage of that as well. But you have to help us to move forward fast. So, with that, I want to introduce our keynote speaker, Satoshi Tadafaro. Satoshi is an incredible man. He basically is the sharp end of the spear of disaster robotics in Japan, and in particular, when the Fukushima disaster occurred, he fielded the first Japanese robot that went in there, and in fact performed better than the robots that we sent there. It was the one that actually climbed up all the way on all the stairs to get to the center. So he's going to talk from first-hand experience about what it was like there. Of course, our disaster preparation goes beyond nuclear power plants, but this is the best example, and I believe the best speaker to talk to us about what it's like in there. So with that, Satoshi.
Thank you very much, Leo, for your kind introduction. It is my great honor to be here to explain my experience. This is a cartoon called in the US. When I was 3 years old, I was a fan of this cartoon, and I enjoyed it very much. And I think this is an opening movie. This is a movie completely different from the US version. Anyway, this is brilliant. And the creator of this cartoon is born and bred in Korea. And so in the NASA world, we have a monument of this gentleman. And he is enjoying it very much. So this is and this is another one. So this type of flight path robots were really popular for many years. And many people are fans of this afterboard. This is really and if you enjoy it. Maybe this is the reason why the many Japanese people like it. And this is another one. And this is HRTC. So at that time, I was really surprised to know more of this very completely involved research studying rescue robots. So we studied the rescue robots from that time. And this is one of the big projects of the Japan Next Ministry of Education. This is called DDD project. I published a book from Springer, so if you're interested, please buy the book. This is a post. And yes, we did several things, for example, a helicopter or some balloons to gather information or distribute sensors, a snake-type robot for the for surveillance in rubber pile or UGVs and some database for gathering information and so on. And this is one of the outcome of this project. The left-hand side is a normal video scope, and but it stops here. However, our active scope camera can penetrate into deep in double pile. So it is a very nice property in the rubber pile and also in the pipe inspection. Okay, it was applied to this construction accident which happened in 2007 in Jacksonville. And for the forensic investigation, it was used, and it could gather evidence, information in 7 meter deep in narrow space, and particularly the shape and direction of cracks and cross-section of plates and so on. So it helped that forensic investigation very much. And this is another case of the real accident. This is a Cologne historic archive collapse, and the active scope camera deployed there, but actually it was not used there. Okay, so this is the list of the response by International Rescue System Institute, which I established in 2002. And we did several things after March 11th. The main things is, one is building inspections by UGVs, and port inspection and the victim search by ROVs. And the third is the Fukushima Daiichi reactor accident response. And this is one of the example of the investigation of damaged buildings. This is a research building in Tokyo University, and we made some surveillance in the buildings 2 weeks after the earthquake. And this is collaborative work with Professor Vijay Kumar, University of Pennsylvania. Maybe he is here. I told him in the morning. But it was really nice collaborative work because this is a Prince, our robot, and this is a Pelican made by Professor Vijay Kumar. And Vijay's robot could enter this narrow space autonomously. However, the Prince cannot because it is too big. However, this Pelican can fly only 10 minutes. So the collaboration between UAV and UGVs are really convincing, promising way for surveillance of the whole buildings. And this is another one, the port inspection and victim search. This is done by Professor Robin Murphy and Professor Tetsuki and from Matsuno in Kyoto University. Anyway, this is a case of the Fukushima Daiichi nuclear power plant accident. I visited in April after 1 year there and took picture of them. So as you see, this is a full of the rubber pile for the Unit 4. And we could enter because the Unit 4, the reactor of Unit 4 did not damage very much, and the radiation was so low. The actual number was 30 microsievert per hour, and human workers could work there. But we could never live there. But anyway, in these situations, our robots should work. That is the real application of the robotic system. Okay, so what the needs of robots in Fukushima Daiichi? One is the mission is stabilization of the system, for example, cooling and the confinement of radiation, and decommission to extract the nuclear fuel is a mission. And then robotic system is needed because the minimization of radiation exposure is very important. There are several tasks, for example, debris cleaning, surveillance and mapping, and instrument setup sampling, shield and decontamination, and material transportation, construction pipes and equipment, and so on. So many problems. There are so many problems, and we should create robotic technology for this purpose. And I really thank the iRobot company who donated 2 hackbots and 2 warriors to TEPCO Tokyo electric power companies. And hackbot contributed significantly to the full shutdown of this accident because it entered into the nuclear building at first. If we didn't have hackbot, we couldn't know the situation inside, and maybe this operation could be delayed significantly. However, there was a problem. The TEPCO people tested hackbot in Unit 5, and they found hackbot cannot go up to the second floor because of the lack of the mobility. Therefore, that was the reason why our research robot, Queens, was used. So this is a comparison between the Queens and the hackbot and other robots. Queens is a research robot, so it has no reliability. However, it has excellent mobility, as I explained later. And hackbot is significantly used in Afghanistan and so on, and for more than 4,000 units are used. So it is very reliable robot, but unfortunately it could not go up to the second floor. And this is a project of the research project which produced the Queens. The main purpose of the Queens is search in confined space where some chemical agents live. And multiple robots enter there and negotiate rapid fire steps and open the door, and then send them gathered information to the operators. That is our mission for this project. And this is research issues which we thought at the beginning. And this is a data flow of the typical teleoperation system. Here is human and here is robots, and they are connected by some intelligence and communications. However, in a disaster situation, mobility is not sufficient and sensing capability is insufficient. Wireless is sometimes very unstable, and the human interface is not sufficient. So we wanted to solve those problems. And we produced the Queens and the Keynote as a previous version of Queens. And we tested this Keynote and Queens in the RoboCup Rescue competitions very much. And in the RoboCup Rescue, NIST designed the test method. The NIST designed the competition arena, and they applied the test method to this competitions. So the Queens got good mobility because of this test method. So we really thank the NIST people, especially Dr. Adam Jacob over there. And okay, so this is another experiment, and yes. Okay, so this is e-defense, the world's largest shaking stage, and we use this opportunity of collapse of 3-story real buildings. We tested our robots with Kobe Fire Department for the entry into collapsed house, or mobility at the collapsed roof, and mobility on beams of roof, and so on. So this type of the real experiment helped us to make the Queens and the Keynote better performance. Okay, this is NIST ASTM performance test. We got a test using this test method, and it helped us very much. And this was the test of Queens at the disaster city in Texas. And it was actually 2 days before the 3.11 earthquake. And at the end of this another project, I wanted to test it at this wooden rubber pile because Kenneth and Chris could not traverse this large, huge wooden rubber pile. This is the size of the 40 meter by 40 meter, and on this day, it succeeded in traverse this rubber pile at the first time. And maybe it is the first time for every robot in the world. And I was really happy at that time, but after that, some very news from Japan arrived. Okay, so this is semi-autonomy of the place and Kenneth. And by measurement by laser finder and using measured shape, it can negotiate in these situations. This uses only touch sensors and distance sensors, but it estimates the shape of the rubber of the raft line, and it can move in this situation autonomously. And this is a 3D mapping, and using this HD scanner using laser finder, we could make this kind of a map very easily. And this is an application to the teleoperation at a disaster city. There are 3D obstacles, so we needed this type of human interface to teleoperate this creature in this pancake crash simulated facility. This is a classification of 3D point cloud. By using some statistical property of 3-point cloud, we could classify the ground and the rubbles and some walls and the pipes and so on. And by this type of user interface, the human operator can recognize what is what in the 3D display. And we developed also the hybrid ad hoc network, which uses wired and wireless network. So using the cable, it is a very broadband, and near the access point, robots teleoperated via the direct connection by wires. But if in distance, it is an ad hoc network, and it is controlled via this robot. And also, we developed some integration techniques to GIS. So we developed GIS that called Dharma and some standardized protocol using GML to gather information into this database. However, this cruise was not intended for the nuclear power plant. So the radiation tolerance was a significant issue there. We asked some specialists, particularly in the space robotics, and we knew there are two types of damages by radiation. One is a radiation total dose, and the second is a single event which change occurs. However, in the case of the nuclear power plant, gamma ray is a major radiation source, so it doesn't have any charged particles. So this is not a problem. So I was really relieved to know this fact, and so we could start the remodeling of the quiz. However, we had some questions. That is, can the consumer semiconductors like Atom, CPU, or CCD, or LiDAR, and so on, can work in the nuclear reactor building situations? And if it is not, we need heavy shielding. And if we'd like to reduce the radiation 1/10, we need 2 centimeter thickness of the heavy materials. So it was a serious problem. So we did those tolerance tests in JAEA Takasaki laboratory, and the result was the weakest sensor was LiDAR. However, if the condition is 100 millisievert per hour and we set the safety factor to be 0.1, it survives 5 days. The main usage of the robot is we use 2 hours in the reactor, and then it's started. And on the next day, we use 2 hours. In such kind of not continuous usage, we concluded that 5.2 days are sufficient. And the communication was a severe problem there because the reactor building has perfect shield to prevent radiation, of course. So we experienced instability of wireless communication very much. For example, the wireless around 2.2 gigahertz of RAP can communicate only 50 meters on line of sight according to the Japanese regulation, strict regulations. Therefore, we plan to increase the power to 1 watt or 10 watts or so, but we didn't know how much power we need. And we knew lower frequency can reach beyond obstacles. However, we didn't know what frequency is appropriate. Therefore, we did some testing at the Hamaoka nuclear plant at rest. And we put the transmitter here, and we tested the connectivity because we had only 2 hours for this testing. We prepared a wireless LAN 2.0 gigahertz 1 watt. This is illegal in Japan under Japanese regulations. And analog video transmitter 470 megahertz 1 watt. This is also illegal. The result was in blue part it was stable, but for the red part it was unstable. If we change the frequency, if we change the power, the result was almost the same. Therefore, we concluded that wireless communication is hopeless, and we can do it only on the line side, and we need wired communication. That is our conclusion. So we remodeled our queens in this way, using some communication cables and so on. Okay, so after that, in June, it began to work in the Fukushima Daiichi. And this July 8th is the second mission for this case. It was really successful. It went up to go up to the second floor and third floor and took a picture like this and measured the radiation. And it helped very much the TEPCO work of planning of the reconstruction in the Fukushima Daiichi plant. And this is captured operator stations, and every 1 second. It is not smooth, but actually it is smooth. As you see, it is going up from the first floor to the second floor. This is front camera, this is rear camera, and this is broader view camera. And this is radiation dosimeter. This says 35 millisievert per hour. This is a really dangerous situation for human. Could you skip to the last one? Yes. Yes. You will see it drops when it returns to the initial. Yes, this is a very slippery because it is an iron steps. But it is very round because it was built 30 years ago, 40 years ago, I don't know exactly. So at first it was rectangular, but it's very round, very slippery functions, and sometimes it is wet. So in this situation, it had to work. That is a real work in the nuclear reactor buildings. And this is the mission on July 26th. And this was really successful because at that time, TEPCO people were planning to set up the double cooling system using a core spray system. So they needed the situation on the second floor. So Queens went up to the second floor and took picture, a high definition picture like this, about the valve of core spray system and pipes and so on. And at the same time, it measured the radiation like this. So it helped their planning of the safest or minimizing the radiation exposure of the human workers. And also, it went up to the third floor, and it is a picture from the second floor to third floor, and it is a landing. And as you see, by explosion, it's a rubble pile. I think it could go up to the third floor, but the operator decided to stop there. And this is a picture. Such movies you can download from the webpage of TEPCO. So if you are interested in, please search in their webpage. That will help to know a particular real situation inside. As you see, most places are the ordinary situations. This is, I think, the second floor. However, on the third floor, it's full of grapples, and at least this landing is full of grapple pile, and maybe the many robots cannot go up through this place. Okay, this is October mission. It was really successful. It could survey, the Queens could survey the whole third floor of the Unit 2, and it could went up to the 5th floor. Okay, this is, I think, the second floor or third floor, and it is surveying like this. And this Unit 2 was not exploded, so it is in the normal situation. However, as you see this number, the radiation is quite high, 10 millisievert per hour. So it is very dangerous for human workers to enter. And please skip to here. Okay. Yeah. Okay, so this is a picture of the 5th floor, and it was really successful because no robots could not go up to this 5th floor. This is called operation floor, and this is a very important information. Please skip to here. Yes. So the Queens opened this curtain by using its arm and entered this place. And it was really successful because it could check the situation of this crane and could measure the radiation. And in some place, it is more than 100 millisievert per hour. And could you skip to this? Yes, to here. And it tried to return to the first floor. However, on the third floor, operator made a mistake, and the cables are hooked to the facility. And please go to the yes, here. And yes, the cable is here, and it is hooked to this facility. So operator tried to unhook this cable again and again, but unfortunately, after that, the cables were cut. So it is a cause why Queens stopped there. And at present, Queens is on the third floor, on the Unit 2. So it is lost, and we have no information. After that, Professor Koyanagi Chiba Institute of Technology prepared second and third Queens. I was independent from the two Queenses. And Queens 2 took a picture of the stopped Queens 1. Anyway, there are several problems remaining. This is a plan shown by TEPCO last year, 1 year ago. And according to this plan, they are making several efforts to shut down and decommission. However, for many of these robotic systems are needed. So this is a list of the something for the robot systems for plant investigation and monitoring. They need mobile platform, UGVs, wall climbing robot, aerial robots, pipe inspection robots, or some swimming robots, and it must have this kind of capability. And they should have some information gathering functions, sensing or light work, communication or teleoperation, and so on. And they require the capability of investigation and monitoring. For example, the sensing of gamma ray source or thermal image and so on. And they need sampling of liquid gas and so on. And they need monitoring of the environment and so on. And they need inspection of similar things. And this is a requirement for the remote robot system for risky works in ground. They need general-purpose mobile platform for work tasks, including consisting of UGV, manipulator, communication, teleoperation, sensing, and it should have some remote tools for tasks. For example, decontamination, or piping, or transfer of heavy objects, or maintenance of machines, or wiring and light works. And yes, there are common conditions and performance and environments. For example, it is extreme environment, so the radiation can be very high and very high temperature or high humidity, and it should turn in narrow space in the ground 1.5 meter and height. It should be 1.5 meter high and 0.9 meter wide. And communication is a problem because it should communicate in narrow reinforced concrete W. And battery should survive more than 4 hours under continuous task execution, and short setup time, easy decontamination, dust-proof, waterproof, light explosion protections are needed. And also, we should consider these points. Work plan for minimizing radiation exposure of workers. This is the objective of using robots. And execution and improvement of robot work, even if low efficiency, would be very important point. And construction machines should be used as mobile platform for heavy works. And teamwork as a system with monitoring robots and others is very important. And it should be general purpose for both unforeseen accidents and ordinary time. And maybe it is a good idea to make obligation of usage of regular plant check. And this is another issues of system integration, standardization, evaluation, performance metric, and key fundamental technologies. We need key fundamental technologies of anti-radiation electric parts and ad hoc stable communications. And also the integration and standardization is very important. Standardization of teleoperation human interface is very important because human workers don't like to spend so much time for training the operation of the robots. And sensor interface is important, standardization is important, and information collection, recording, and database should be standardized. Test method should be standardized with test field for performance evaluations. Those are very important points. Okay, so robotic systems are very considered to be useful tools by general public. Actually, I think the Eastern Japan earthquake was a historical first case where many robots were used. So in the future disasters, it become a common useful tools. What is the robotic solutions? That is the accessibility to the disaster information is very important point. So at first, information gathering at inaccessible places the information gathering at inaccessible places is very important. However, I think there remains several fundamental problems to be solved, For example, if we want to check the situation at high places or narrow confined space, we have similar problems. For example, wall climbing robot can move on the flat walls very easily, no problem. However, if we check thorough whole plant, we cannot do it because the 70% we have no problem, but 30% is maybe all the robot cannot access them. So we need such kind of solutions. And if 30% is inaccessible, user says, oh, we cannot use this. So this is a problem, I think. So what is the research issues? There are similar issues, mobility and positioning, sensing and mapping, light task execution, communication, teleoperation, autonomy, of course, and anti-explosion, durability, lightweight, and so on are very important. On top of that, reliability is a necessary condition for that. Therefore, I think the science technologies for synthetic systems, including human under severe constraints, needed. This is never a simple problem of mobility nor combinatorial issues for applications. And I hope this DARPA robotics challenge can contribute to the development of this science and technologies. This is very important issues, I think. Thank you very much for kind attention.
Yeah, so let's take some questions, and Toshi, if you could please, with the webcast, since they won't hear the question well, once you hear the question, just repeat the question and then you give the answer. Okay? Good question.
The question was how is the phase 2 as the next robot? Actually, I don't know very well because Professor Koyanagi developed that robot. But the phase 2 was some remodel of phase 1. This is substantially the same, but it has a problem of the, for example, the cable handling and some durability issues and payload, limitation of payload. Such kind of basic problems are solved in phase 2. The question is, what is my dream robot? My dream robot is apparently the cartoon robot, which I showed at the first. Yes, we need a mighty robot, but it should be inexpensive. That is at the same time, yes, if you could develop such kind of solution, I really appreciate it.